theory. Somehow seems pretty appropriate to finish this series with a little bit of serious fun, I guess you could say. I'm going to pick, because it's the one topic within game theory that's manageable and beautiful, two-person games. So there are two opponents, no coalitions. If we have a seven-person game, then one group can form a team and go against another group, and it becomes very complicated. And also the game will be zero-sum. Whatever the two players, we might as well call them R for the person who's going to choose a row, and C for the person who's going to choose a column. So I have a matrix. I start with the payoff matrix. Let me take an example that's 2 by 2, just to explain the rules. So maybe the entries are 1, 2, 4, and 7. Okay. So R, the person who R chooses a row. C chooses a column. That identifies a number, and that's the payoff to R. So whatever. So R chooses row I. C chooses, in the best way possible, column J, and R gets that amount, Aij, that entry, from C. Well, this game is certainly stacked against C, right? All payoffs are positive in this case. There's no reason. If I subtracted 100 from all the entries, what would be different? Well, it'd be stacked against R. Well, if all the entries were negative. But the strategy wouldn't change. I mean, if it was 100 subtracted from all entries, then it would be like the same game, and then C would get 100 each time. So it's the strategy that we're looking. We're looking for strategies, looking for the best strategies, best optimal strategies. That means which row should R choose? Well, that's clear. In this case, what's R's reasoning? And which row does he choose? Row 2. And the reasoning is, whatever C does, I'm ahead. Right? If C chooses column 1, I'm ahead. If C chooses column 2, I'm ahead. Okay. And now what's C's reasoning? What does C choose? C chooses column 1 with the same reasoning that whatever happens, whatever R is doing, it's better to be in column 1. Okay, so that's an easy case. The best strategies are completely clear. They're what I would call pure strategies. So this is a case where the best strategies are pure. Now let me just change a couple of numbers here. Put the 4 here and the 2 and the, well, let me change the numbers around a little more. All right, that's a more reasonable game. Now what? Now what? Think about the strategies. We know the rules of the game. What should R do? Well, not clear, right? Not clear. Because if R, so what will happen? If R likes the idea of winning 7, right? So if R chooses this row, what will C do? C will notice. We're thinking of this game as being played repeatedly, independent plays. Every play is independent, but the players know what's happened from the their decreasing pile of, or increasing pile of income. Okay, so yes.
I'm sorry, I don't get it. So R chooses
It,
C saw that?
no, sorry, I should have said, no, they choose at the same time. They choose at the same time. Would C always choose column 1? Oh, did I not improve it? Yeah, C would, yeah, so what, all right, let's follow this example then, which you're right, is a relatively easier one. C would always choose column 1 on the basis that whatever R did, 2 is better than 4 and 1 is better than 7. Good. And then what would R do, thinking this through? R would say, look, C is, he doesn't know what C is going to do, but he can think it through. He can think the same thoughts that C thinks. So he realizes that C is going to choose column 1. So R is therefore going to choose row 1 all the time, and we'll be there. We'll be there. Yes, right. So there's another instance, less obvious, but oh yeah, no, actually that one, yes, that's pretty clear. Okay, now can you help me make it harder? Switch the 2 and the 4. All right, switch the 2 and the 4. Okay. All right, now let's put ourselves in the place of R. R says, well, what would you do if you were R? Let me just ask you. If you were R facing this game, what row would you choose? Well, say either one.
Yes,
1. You would say, choose row 1. Okay. Well, if you kept choosing row 1 over and over, I mean, if that was your strategy, then C would choose, because C would look only at that row, C would choose column 2 over and over. But then what would you do if you were R? Hey, we got this guy nailed, right? He's choosing column 2. I'll just slip in row 2 and get the 7. Right? But that happy feeling won't last very long, because as soon as he says, C says, wait a minute. Now he's switched to column 2 and I'm paying out 7. I'll switch to row 1. So then he switches to row 1. All right, and then R notices, okay, he's on row 1. I'll go on column 1. So C would switch to column 1 and not pay off 7. Then R would go back to row 1 and pick the 4. And then then C would go back to column 2 and be paying off 2, and then it would go on, right? So here we're really at the critical moment in this lecture, right away. What could be an optimal strategy, or I'm not asking for the optimal strategy, precise answer, but you've got to have some randomization. Yeah, weighted dice. That's exactly right. Each player ends up in this. As soon as we take a case with the numbers a little like this, which would be the typical case, then the best strategy is you cannot tell that other person. You can't give that person any information about a particular play of the game, because if you pass up information about a particular play of the game, then your opponent will use it. So the best you can do is, and you can do it in front of your opponent, is flip a coin, a weighted coin, so that R will choose these in proportions x and 1 minus x. So R's choice amounts to selecting the fraction x of the time of the number of plays that he'll choose row 1, and the remaining fraction row 2, but randomly. And C, similarly, has to randomize, or is going to pay the price So C will choose some x and y are between 0 and 1, so that, you know, this is some fraction like 1/3 and 2/3 of the time. I don't know if that's right. This is some fraction like 2/5 and 3/5 of the time. Well, that doesn't sound right. That would come to 7 quite a lot. So anyway, that's the idea. So the best strategies are what I would call mixed strategies. Mixed meaning you mix up the number of rows, the choices. You mix your choices in a random way. And of course, I don't know, I mean, every poker player would, let's just think about other games for the moment. Does this, if we think of poker, does this fit the way you would do poker or blackjack, or I don't know what your favorite game would be. In poker, well, let's just take poker. Well, so there are many, many more strategies. The trouble with most realistic games is the number of pure strategies. See, this could have been a 3x3 matrix, or it could have been a 3x5 matrix. We could have given R 3 choices and C 5 choices. And in poker, of course, the number of different strategies would be overwhelming, because we have to have a strategy for each situation. But generally speaking, poker is like this in that you might bluff. So bluff would be, bluff would be maybe in the case of C going this way, and taking a chance that anyway. Taking a chance that for some fraction of the time, R will be making this choice, and you'll only have to pay 2. So I want to know X and Y and the average payoff. So what's the average payoff? Yeah, maybe I better call these X1 and X2, because there could have been 7 of them. And I'll call these Y1 and Y2. So the point is, of course, that the sum of the x's is 1. All the x's are, of course, greater or equal to 0. And they add to 1. They're probabilities of choosing different rows. And similarly, the y's are all non-negative, and they add to 1. That's clear. Okay. But now, what is the payoff? If I've decided on playing these fractions, the rows, and C has decided on those fractions of the columns, how often does a 4 get chosen? How often is the payoff 4? X1, Y1. Because these are independent decisions. So the payoff would be 4 X1, Y1. That would account for the fraction of the time. The fraction of the time that we have a choice of X1 and Y1 times the 4 that you pay. And then what are the other terms? Well, there's a 2 from X1, right? The payoff of 2 occurs in the fraction X1, Y2, and the payoff of 1 occurs in the fraction X2, Y1, and the payoff of 7 occurs in the fraction X2, Y2. And I'd like to have a nice matrix form for that. And I think it would be just Y transpose AX. Can I write that? That's Y1, Y2, multiplying the A, 4, 2, 1, 7. Oh, no, I've got to get it's X transpose AY, isn't it? Because I've got to get X choosing rows. These have to multiply the rows, and these have to multiply the columns. Is that right? That if I do that multiplication, the X1 will multiply the 4 and the Y1. The X1 will multiply the 2 and the Y2. I'll get the 4 terms, and that's the... I'm just getting a nice notation here. So, what is the job of R? The person who's choosing the rows. Well, he's the person who's getting the payoff. So he's trying to maximize the payoff. So maximize this payoff, X transpose AY. Wait, choose X. Let me say it in words. Or use more words here. Choose his. He's choosing his row fractions to maximize the payoff X transpose AY. Okay. But now, and of course he has the constraint that his fractions should add to 1. That's clear. But what's really constraining him here? What is he actually? He has to, when he chooses an X, what will Y do? Because after a year or two, Y is going to notice what those fractions are. I mean, now we have to think about the big picture again. We've decided that you have to decide on fractions and randomize, right? But after 1,000, 2,000, a million plays, that X is going to be known to Y. He's going to see pretty closely what the fractions are. So this will be known to Y. So what will... once that's known to Y, what would Y then do? The C then do, the choice of columns? He would minimize. Yeah, so Y is going to minimize. So he has to maximize this, but has to recognize that Y is. Let me show you what's up here. One of them is trying to maximize over all the X's. This is the minimum over the Y's of the payoff. And the other is trying to save money. He's trying to minimize over all the Y's, but has to realize that whatever choice he makes, X is going to take the maximum. Those are the two calculations. This is the calculation that R has to make. This is the calculation that C has to make. So it's dual, so we could just think about R. So R has to think, okay, I'm going to take the best X, but it has to be best against the worst Y.
The worst from his point of view.
Sorry?
The worst from his point of view.
The worst from his point of view. That's right, the worst from his point of view. Okay. Now, if I was strong enough, we could work this out. I don't know if, let's see. Can we try to see if we could do it? This is the payoff written up in full. Okay. So basically what does X have to do? He has to present Y he wants to present Y with two columns where Y has no reason to go one way or the other. I think in this case, see, what will Y usually get? When Y, think about it this way. Suppose Y chooses column 1. What can he expect the payoff to be on the average after zillions of plays? 4x1 plus 1x2, I think. Is that right? If we're in Y's position, the payoff to Y in choosing column 1 would be 4x1 plus 1x2. That's the payoff from column 1. The payoff from column 2 is 2x1 and 7x2. And I think x wants to adjust those so that those are the same. I think. It seems right to me that if provided this gives non-negative x's. So what does that tell us? That tells us that 2x1 is 6x2. Is that what we get out of this? This leads to subtracting the 2x1. That gives us 2x1s is 6x2s. It looks to me like this ought to be the bigger one, 3/4, and this should only be 1/4. I think that's the conclusion.
So he basically gives y no opportunity to change.
No, there's no reason for y to change, because if he doesn't do it that way, y will change. So then the average payoff, when x1 is 3/4 and x2 is 1/4, is 3/4. What do I get then for those numbers? Just 1/4, and that makes 3. 3/4 times, that's 3. I think we get 3 1/4. And I believe that's the value of the game. You can say, wait a minute, I haven't figured out Y's strategy yet, and that's true. Let's see, so let's figure out Y's strategy in the same reasoning. Okay. So Y's strategy will be, if row 1 is chosen, the average payoff is 4y1 plus 2y2. Whereas if the second row is chosen, the average payoff will be y1 plus 7y2. And if he makes those equal, then R will have no reason to choose one row over another. So what would that give us? That'll give us 3. That leads to 3y1 is 5y2s. So they're in the ratio of 5 to 3. So maybe 3/8 and 5/8 and 3/8. 5/8 and 3/8. Because then 3 times 5/8 does give 5 times 3/8. Now I think we've got it. So there's a particular game that's solved. That's a particular game that's solved. And so the first and most important point is the point we saw earlier, that in this game a mixed strategy is the best. A randomized mixed strategy, if there's any pattern, the opponent will take advantage. Here there's no pattern, except the only pattern is this is 3/4 of the time and this is 1/4 of the time. And then if you plug those numbers into the payoff, you would get 3 1/4. I'm sure. We could. Yes.
This business of it being best to pick a point where y doesn't want to change.
Yes.
Is it clear why that is? Is that because there's some quadratic somewhere that?
I guess there is. Somehow, yeah. That's probably it. So this is a what the end result is the fact that the best X can do is to guarantee himself this amount. And the best Y can do is to guarantee to not pay more than that amount. Because he's making that as small as he can against anything X can do. And the beauty is this minimax theorem, that this minimax equals the maximin, that's the duality, of course. That the two players are somehow locked in this dual picture, and that is that holds. Now let me. I don't want to. So this was a case where a mixed strategy was right. So that for both of them. Let's go back to what was an easy case at the start, and just think it through again. So again, R and C, and what did I have then? Something like, say, 1, 2, 4, 7. And then what were the best strategies for this game? This was the easy game. Remind me, what should R do in this game? To row 2 all the time. So his fractions should be 0 and 1. And what should C do all the time? Choose column 1, so his fractions should be 1 and 0. So this is y1 should be 1, and x2 should be 1. So there's a case in which, because we were bumping up against the limits, the 0, 1 limits, we didn't find a mixed strategy. This is like the key with these inequality constraints. Either you're kind of in the middle, where you're in the middle, and you could go either way, a little more on column 2, a little more on column 1. When you're there, it's like being in the middle of a function, say, like this. It's like minimizing. When you're in the middle, you could go either way, and a derivative has to be 0. But if we were maximizing that function over this interval, what would be the situation? The maximum would be at an end, and the derivative isn't 0 there. It's like you have an inequality. That can only be a winner for the guy who's maximizing if the derivative is positive, because then you wouldn't want to come in, which is the only direction you would be allowed to move. So we're talking about maximum, minimum optimization with constraints that if the constraints are active, if you're at the edge, then the constraint is an inequality constraint because there's only one way you can move. Where if you're at the center, the constraint is an equality constraint. Some derivative has to be 0 because you could move both ways. So this was a case where you could move both ways. So equalities had to hold. We had equations like this. We made it so that C had no reason to prefer one or the other because he could move both ways. Here, we're facing C with a choice where he's losing 4 all the time, and yet sort of we're at the edge. If he would like to choose this even less, but or even sort of, well, anyway, we're at a 1-0 situation for both of them, in fact. So that, do you see what I'm saying? That R is not presenting C with an equal choice. If R keeps choosing this row, then C's choice is to lose 4 or 7. So he always picks losing 4. There was a case there where there was an inequality. If 4 was less than 7, therefore all the marbles went on to column 1. This was a case where in either direction it didn't matter, and we ended up with mixed strategies. Maybe that's the theme of optimization with inequality constraints. And maybe I express that now in a language that's not game theory, but typical problem of minimizing some cost function subject to some inequality constraints. So now I'm really, in these last minutes, speaking about optimization as we really know it. we're minimizing something. That's optimization. There are constraints. They can be nonlinear. That can be nonlinear. And they can be inequalities or equations. So there is like a general optimization problem. And how would you handle such a problem? That's not an easy problem. Because you don't know, if you knew, you see, if you knew, so the best x, I'm looking for the best x star, the winning x. We're in any number of dimensions here, and we have any number of inequalities. Then, if we knew that the best x, if we knew where it was hitting the boundary, if we knew in which components a of x star was equal to the corresponding b, and in which components it was less, we would be golden. Because then we would have equations. Do you see? Unfortunately, we don't know that. So x is n different numbers. So we've got n numbers to choose, and b is m different numbers. So we've got m inequality constraints, and my point is, if we knew where the equalities were, then those would give us some equations for x star. And then, and we knew the other ones were inequalities, then we would know some derivatives in those components were zero, because we would be, in those components, we would be able to go left or right, and therefore a derivative with respect to that would have to be zero. We would have a set of equations we could solve. But we don't know which constraints are active and which are not. That's what it comes to. An active constraint is one where you're pushing at where equality holds. You're right up in my picture here. There's an active constraint that the x can't go beyond that value. That's forcing us to be there. And if we knew that, then we could just look there. If we knew it didn't hold, we could look, in the middle, maybe, whatever. So but it's a tough problem because we don't know, and we cannot check all possibilities. The number of possibilities is too great. So you have to introduce this trick of introducing Lagrange multipliers is the brilliant idea. So the Lagrange multiplier, the Lagrange thing, then you bring in some multipliers. Why? You do that by taking the cost and adding to it these y's times the constraints. And the nice way to write that is y transpose b minus a of x. So somehow, yeah, I'm not going to be able to describe Lagrange multipliers in one go here. But the trick is to bring in these new variables that seem very mysterious, and they have to be greater or equal 0. And you look for a maximum or you look for a minimum with respect to x and a maximum with respect to y. So it actually is a nonlinear type of game theory. So in the end, you look for the minimum over all the x's, because that's the problem you finally wanted to solve. But then there's a maximum over all the y's, and you get this function to work with. I think probably what I need to say about optimization is what I've said already, that it's a subtle type of mathematics. The algorithms have to play back and forth between reducing the cost and satisfying the constraints, And I think you wouldn't want to write your own software to do this. I mean, this is for professionals in that field of optimization to create software to solve problems. So maybe it's worth saying that that a major activity in numerical analysis over the last, say, generation has been to create software that that could be widely used, that's reliable, efficient, stable algorithms, and produce it. I mean, so the packages that, so LinPack would have been a typical package of software. That was for solving linear equations. And then you would have a special code if the matrix was symmetric. You would have a special, even more special code if the matrix was positive definite. You'd have a special code if it was tridiagonal. You would just have it's a suite of linear solvers to handle different cases. And IcePack, which actually came first, is for the eigenvalue problem. Again, dealing with symmetric or unsymmetric matrices, all these cases. And now, in this problem, in this case, there will be a package called MinPack. And you can see the human invention. So everybody who, if you want to do conformal mapping, well, look for a package that that does it. If you want to do, if you want to use parallel, this is now replaced by LAPack as a upgrade, and then replaced further by a parallel package if you had, or if you wanted a software that did it in parallel. And maybe I'm saying what you all know. Just. So MATLAB would use that particular package. So MATLAB, the MathWorks people are not the original creators of these packages. And the really nice thing about this area of numerical linear algebra is that these packages have been created by people and put out for free. So MathWorks is free to use, to incorporate that package in MATLAB. And then, of course, MATLAB is not free, far from free. The one source of free ones, there's a email, probably a web page also. That's sort of net library. Often library is the word for a whole collection of packages. NetLib was maintained, I think it's oakridgenationallab.gov. You might, and there would be a web page now, which where originally it would have been, you would send a message like send index or something would be the subject of a message to NetLib, and you'd get a list of organized list of some of the things that are available. So that would be one source, and then there are commercial sources also. But there are these, I would always look first at these free sources. So haven't come close to listing all the packages. So like everything ODE pack, right? What's that going to do? It's going to solve ordinary differential equations. And many, many, many more. It's an interesting world, these packages. So So MATLAB, of course, has these packages in its system. Say for the finite element method, there'd be a FemPack, I'm sure. Actually, that reminds me, a new company, which some people in Sweden wrote a finite element code for solving partial differential equations called FemLab. And they decided, okay, we'll try to, because that's a big job to write PDE packages. That's a multi-person, multi-year task and very expensive. So they've actually established a company here in Burlington, which I understand is making a go of it. The Swedish company was ComSol, Computer Solutions. So that's the company corresponding to MathWorks, and then this is the package they sell for solving partial differential equations by finite elements. And MATLAB has a PDE package, sure. I don't. I hate to answer that question, which is better on a permanent. Let's say they feel it's better, right? Right, and other people too. Yeah, because I mean they've focused on that, and of course you're seeing here, as you've seen in the lecture, the range of problems. If we're solving a linear system, that's a pretty well-defined problem. Of course, we have these cases within it of banded matrix or positive definite matrix, so we need special subroutines. To solve partial differential equations, those come in such variety that the job is to organize it. What are you going to allow the user to ask for? I mean, what are you going to supply? Well, you pretty much have to allow the user to tell you the region somehow in which they want a solution, and to tell you what the equation is, and to tell you what the boundary conditions are. You have to allow the user to tell you the necessary information, but then you want to take the decisions on the mesh. The program should do that. You want to relieve the user of that. Maybe the user specifies some accuracy that they're willing to, that they insist on, and then that will control how many mesh points you have to take. But so that's become a central part of the world of numerical analysis. Scientific computing is as these problems get kind of into the way a book can be written when a subject is kind of getting there. So software can be written. Yeah. So that's and then of course there are the other problems that haven't reached a stage where we don't know. People are finding better ways all the time, so that investing in creating a permanent package, the time isn't ready yet. Yeah, so that's part of the subject. This is the part of the subject, thinking about my own subject now, where you're trying to create packages without knowing the problem, right? It's the user who knows the problem. You're trying to create packages that will solve many types of problems. I distinguish that from the other part of the field, which is gaining the name computational science, where the numerical person is right in there with the biologist, or the chemist, or the chemical engineer, or the signal theory person, right in the problem and knows what the problem is. So that's in a way a harder thing for the computational person, to get right in there and sort of have a mixture So this is computational science. It's some mixture of you need to know the science, that's the point, plus you need to know computing. So computer science, really. You need to know what you can get the machine to do efficiently, and you need to know the numerical. You need to know about numerical algorithms. You have to have a feeling for which way or which are stable. You know, what's a good approach to this. And so this computational science is becoming a sort of very important theme, say within SIAM, the society I'm most involved with. Is more and more people, for example, in biology, it's not good enough in biology just to sit back and offer LAPAC. You have to be in there in the formulation and of the problem into an optimization problem. Say, I mean, protein folding is an example that's very much in the air now. So proteins, you know what you're starting with, but they fold themselves to get into a position of minimum energy, with some constraints, of course, that atoms can't and molecules can't come too close, and that's turning out to be a very, very large optimization problem. These numbers M and N are enormous, and if you don't know something about the biology of proteins, you can't write the best code. So you really need to be involved with the science, with the algorithm, with the stability and analysis of the algorithms, and with the fast execution of them. So that's really maybe where applied mathematics has come. That classical applied mathematics was the theory of differential equations, Bessel equations, and all the others. I'd maybe let Bessel stand as an example of the whole subject. And many people would still, that's the center of their work. But the recent years have brought other parts of applied mathematics, and they're in a kind of uneasy equilibrium now. Journals of applied mathematics, some journals will emphasize the classical issues, others will be purely numerical about given a job, how would you do it, and then others about what's the job. So that's somehow a summary of what I hope these lectures brought out. So with my own background, those were not equally balanced. I tried to identify, mostly I think, in order to achieve something within the hour, try to identify a problem and then ask how to tackle it. So I didn't, partly because I wouldn't know how to do it, go way, way back to the origin of the problem. That's more than I could do in these lectures. But I want to emphasize, I want to emphasize the importance of that, the modeling of the problem. Given the physical problem, creating the model, creating the equations is a very crucial and non-trivial step, and highly valuable. And that's part of our subject too. Well, this is maybe the right time to thank you guys for making these lectures possible. I enjoyed it all, and it's, as you've seen, suggested problems, and also it's suggested writing that's going to affect the courses and I hope a new textbook. So thanks. Right.